One of the reasons we fear nuclear radiation is we can't see it. It was Henri Becquerel who took a photographic plate, enclosed it in opaque paper, and placed a sample of potassium uranyl sulfate on it. He stored it inside a dark drawer for several days. The result? An exposed photographic plate, the first visible evidence of nuclear radiation. It seemed that the rays were being emitted by the sample and fogging the plate. Rutherford and Villard showed that this radiation actually consisted of three different types: alpha, beta, and gamma radiation. The most obvious difference between them is their penetrating power. Alpha rays are easily stopped, beta rays less easily, and gamma rays have a great penetrating power. Researchers soon found other differences. When a radioactive sample was exposed to a magnetic field, the resulting pattern showed that each of the three forms of radiation had a different electrical charge. Eventually, an alpha ray was identified as the nucleus of the helium atom. Beta radiation, a stream of electrons. And gamma rays were photons of electromagnetic radiation. This, however, did not solve all the mystery surrounding the radioactivity. What happens to the substance that emits this radiation? It was Ernest Rutherford and Frederick Soddy who first suggested a process called radioactive decay. Atoms emit radiation. In the process, they are spontaneously transformed into atoms of new elements. This change from one element to another, called transmutation, had obsessed alchemists in the Middle Ages. Rutherford and Soddy claimed that transmutation occurred naturally during radioactive decay. To explain this process, we must examine it at the atomic level. When radiation was first discovered, the atom was viewed as a sphere, which contained both positive and negative charges. Advances in the understanding of radioactivity went hand in hand with advances in the understanding of the atom. Rutherford suggested the mass of the atom was concentrated in a very small space called the nucleus, which was positively charged. During the 1930s, scientists realized that the nucleus consisted of positively charged particles called protons and neutral particles called neutrons. It was the number of protons that determined the identity of the atom. They also discovered that the number of neutrons present in the nucleus could vary for atoms of a specific element. These different forms of an element were called isotopes. The element hydrogen has three known isotopes. The structure of a specific atom is usually represented in symbolic form. For example, the element lithium has 3 protons in its nucleus, and so is assigned an atomic number of 3. The most common isotope of lithium has 4 neutrons, making a total of 7 particles in its nucleus. Consequently, it has a mass number of 7. When lithium undergoes a chemical reaction, it is not the nucleus, but the electrons which play the biggest role. It reacts with fluorine by transferring an electron from one atom to another. Note, however, that the nucleus remains unchanged. Electrons may also be shared between 2 atoms. As in all chemical reactions, the nucleus remains unaffected. Radioactive decay, however, involves a change in the nucleus itself to produce one or more kinds of radiation. Consider radon-212 with 86 protons and 126 neutrons. When this atom undergoes radioactive decay, an alpha particle is ejected, producing a major change in the nucleus. The nucleus that remains has become polonium-208. In other words, from radon, the emission of an alpha particle results in a transmutation to polonium. Now let's look at an element that radiates beta particles, such as carbon-14. You might ask, how is it possible for a nucleus that consists of positive protons and neutral neutrons to emit a negatively charged particle? During radioactive decay, one of the neutrons in the nucleus changes into a proton and an electron. This electron, or beta particle, is emitted from the nucleus. The nucleus that remains has one less neutron and one more proton, which transforms the atom from carbon to nitrogen. Let's watch it happen again. A neutron changes into a proton and an electron, and the electron is ejected from the nucleus. The third form, gamma radiation, may occur by itself, but more often in the company of alpha or beta radiation. The isotope phosphorus-34, for example, is radioactive. When it undergoes radioactive decay, it releases a beta particle, as well as a photon of gamma radiation, leaving behind a new nucleus, which is an isotope of sulfur. When Becquerel first discovered radioactivity, it appeared to him that radiation was emitted at a constant rate. Careful observation, however, showed scientists that the strength of radiation gradually declined over a period of time. If we examine a sample of the gas radon-212, we can see how and why this happens. When radon-212 undergoes alpha decay, the result is polonium-208. During a 24-minute period, half of the radon-212 nuclei undergo radioactive decay. Each nucleus emits an alpha particle, and in so doing is transformed into polonium-208. In the next 24-minute period, half of the remaining radon-212 nuclei undergo decay, and so on. In other words, during each 24-minute period, half of the remaining radon-212 undergoes radioactive decay. For this reason, radon-212 is said to have a half-life of 24 minutes. A graph will show that as time goes on, the activity decreases. During each 24-minute interval, the amount of radiation given off by the sample drops in half. The half-life for each radioactive element is unique and can range in value from a fraction of a second to billions of years. There is, however, one major mystery remaining. What produces the energy released during radioactive decay?